Welcome back. All right, today we're going to look at different ways of solving consistency arcs, constraint satisfaction problems. All right, so here's the example we ended up with last time. Just play with it and see whether you can work out what to do. Pause and see if you can find a solution in here. Okay, so what we're going to do is we're going to look at what are called consistency algorithms. And the idea we're going to do is we're going to prune the domains as much as possible before selecting values from them. So in our search, we just selected values blindly. What we really like to do is to prune as much as we can. So the simplest way to do this, the variable's domain consistent if no value of the domain of the node is ruled impossible by any of the constraints. So let's look at this previous one as a scheduling example, domain consistent. Well, let's look at this. The domain of, we have a constraint that says b is not equal to 3. But if you look at the domain of b, where it's 1, 2, 3, or 4, we know the domain of b cannot be 3. We know b cannot be 3 because that's one of the constraints. So we can remove 3 from the domain of b and not remove any of the constraints. And we can do this once and for all at the very start. Okay. Similarly, c is not equal to 2 is a constraint. We can just remove c from the domain of, we can remove 2 from the domain of c. All right. All right, so what we're going to do is we're going to draw something called a constraint network. So we're going to have an oval-shaped node for each variable. There's a rectangular node for each constraint. So we're going to have two different types of nodes in this network. There are variable nodes and constraint nodes. And this is the domain of the values associated with each variable node. So each variable node is going to have a domain of values. And there's an arc from variable x to each constraint that involves x. And an arc we're going to write as this pair of x and the relation. This is our algorithm, we're going to do this. So that, for example, the constraint x is less than y has two arcs. There's the relation between variable x and x is less than y, and the variable y and the constraint x is less than y. The constraint x plus y equals z has three arcs associated with it. The arc between x and the constraint, the arc between y and the constraint, and the arc between z and the constraint. So here is this network that we did before. So there's variables, a is 1, 2, 3, 4, b is a node over here. We've removed the value 3 from b. So it has the values 1, 2, and 4. Okay, and similarly d, now the constraints that says b is not equal to d is a constraint between variables b and d. Similarly, c is less than d is a constraint between the variable d and the variable c. Okay, so let's give an example of doing this. So what I'm going to do is to show you the AI Space 2 consistency algorithms. So what you want to do is to go to notebook/CSP, if you look in the top left here, and on Arc Consistency node. Okay, so if we run this Jupyter Lab page, we can get to this, we can start running it. We're going to run this, we're going to run, load them, reload. I just keep clicking through, and eventually we get to a graph that looks like this. I'm going to increase the size of this text size to make it bigger, and I'm going to increase the line width because the line width is going to be important to us. So if A is 1, 2, 3, B is 1, 2, 3, C is 1, 2, 3, A is less than B, and B is less than C. Okay, so that's going to be the problem we're going to look at. So now we're going to look at this arc here. So if we look at the relation between A is less than B, and A is 1, 2, 3, and B is 1, 2, 3, the fact that A is 1, 2, 3 means A cannot be 3. Right? Because if A is 3, then there's nothing in B there's no choice for B. So A, because of this, there's no value for, if A is 3, there's no value for B, which A is less than B. So if we click on this arc here, it's going to make this arc consistent. So to remove 3 from the domain of A. Okay, and that's what's going to be called arc consistency. So there's no 3 in the domain of A because there's no. So we can remove 3 from the domain of A because when A is 3, there's no value for B, which makes this consistent. Similarly, this one here, so look at A is less than B, B is 1, 2, 3. If you think about this, you go through the values of B, well, B could be 3. Yes, if 1 or 2 works. 2 If B is 2, then the value 1 works for A, that makes A is less than B. But if B was 1, there's no value for A that's less than that. So we know that just from this constraint in B, that B cannot be 1. Okay, so we're going to make that arc consistent. Notice when I clicked on them, they checked from blue into green. Green means they're checked. That's arc consistent. So it means for every value of B, there's a value for A, and it's vice versa. That means here. Okay, now let's go here. B is 2 and 3. So let's look at what C can be. B has to be less than C. Sorry. Let's look at this right arc here. So we're going to prune C based on this. So what could C be? Well, C couldn't be 1 because there's no value for B that's less than 1. There's no value for B that's less than 2 either. The only value possible for C is 3. Okay. Now look at this last remaining blue arc. B has to be less than C. Okay, so the only value for B is, yes, you're right, is 2. Notice these three green. Now this one here just turned blue. Why did this one turn blue? Well, this one turned blue because the domain for B was reduced. So we don't know it's arc consistent anymore. Indeed, here you find that the value for A is 2. There's no value for B which satisfies it. So we click that. We find out there's a unique solution to this. Okay, so you can often solve problems uniquely in doing this. Let's look at a different example here. Let's go to CSP Simple 2. All I'm going to do is just edit this file, and I'm going to rerun it, and I'm going to get a different graph here. I'll make the text size a bit bigger so you can see it, because it's more fun. All right, so now again here, A is less than B. A cannot be 4. A is less than B, so B cannot be 1. We have a constraint here that says B is not equal to 2, so we're going to say, we're going to remove 2 there. Okay, B is less than C, therefore B cannot be 4. And B is less than C, therefore C cannot be 1, 2, or 3. And then we have A is less than B, so here we haven't reduced the domain. In fact, here there are 2 solutions. There are 2 solutions here in this solution. So if you get to arc consistency, maybe there's more than one solution, maybe there's not. Okay, let's now look at this one we did before. Let's copy CSP extended 1. There's another example we can do. I'm going to just copy and put that name in there. I'm going to run this again. So I'm going to run this, and I get this network as which we had before. So now I'm going to run this network. I'll make the text size a bit bigger so we can see it, and make the lines thicker. So now we're going to do the same thing again. C is not equal to 2, so I'm going to remove 2. C is less than D, so C cannot be, so D is 1, 2, 3, 4, C is 1, 3, 4. C has to be less than D. So C cannot be 4, right? So we're going to move 4 from it. C is bigger than E, right? And 1's not bigger than anything in E, so we're going to remove that. We end up with C as 3. Okay, now C's got to be bigger than E, so E's either 1 or 2. Okay, we're just going to do these in arbitrary, doesn't matter what order you do them in. These blue arcs, we can just do this. So C is less than D. Okay, and C is 3, so D must be 4. Okay, now D is bigger than E, and we'll notice that's solved. D is bigger than E, well, D is 4 and E is 1 or 2, but that's true for all 1 or 2. Okay, B is not equal to C here, this one here, so that's C is 3, so here B is not equal to 3. B is not equal to D, so we don't prune D because there is a value for B there's a value for B that's not equal to 4. So, but here we want a value that's not equal to 4. Here we can not equal to 3, but it's already solved. When A is different to B, well, for every B in 1, 2, there's a value for A which is different, and similarly there. For every value of A, there's a value for B that's not equal. If we now look at A is equal to D, well, this D is 4. As soon as we have this, we end up with that has to be 4. A has to be bigger than E, so that means that doesn't prune E and it doesn't prune A because they're all consistent. Now B has to be bigger than D. So if E is 1 or 2, right, then E cannot be 2 because there's no value for B that's bigger than 2. So we can prune that. And similarly, we can prune this. And now we have to check the remaining constraint. Now we're going to check the remaining constraints. 2 is not equal to 4. So that's satisfied, that's satisfied. A is bigger than E, D is bigger than E, B is not equal to C, and C is not equal to D, E, and B is not equal to D. So if you looked at that before, you should have said, there is a unique solution here. Okay, so we'll play with that in here. Okay, so I just went through an algorithm called the arc consistency algorithm. Okay, so what we did is an arc is arc consistent if for each value of x in the domain of x, there's some value in the domain of y such that r of x, y is satisfied. That's what I was doing. So network is arc consistent if all of its arcs are arc consistent. And so what we're going to do is if an arc is not arc consistent, all the values x in the domain of x, for which there's no corresponding value for the y in the domain of y, can be deleted from the domain of x to make it arc consistent. And that's what we kept doing over and over again then. So let's look at this algorithm. So the algorithm is the arcs considered in turn, making each arc consistent. When an arc has been made arc consistent, it does it ever need to be checked again? We'll talk about that in class. When does it need to be checked again? And so here's the algorithm we're going to do. We'll explain this in more detail. For each variable, we're going to get a domain. We're going to start with this variable d of x, which starts off as a domain of x, and then we're going to start pruning it. Then there's all the arcs that we need to do. These are the to-do arcs. These are all of the set of xc such that x is such that c is a constraint and x is in the scope of this constraint. And we're just going to keep looping through these to-do arcs. We're going to select and remove an arbitrary element for xc from this one. And we're going to suppose the scope of c is, these are all the variables in c. And now we're going to compute the new domain of x. Well, the new domain of x is the set of x, such that x is in the domain of x. And there exists values in the other variables such that the constraint is true. Okay. And if we've changed the domain of x, if the new domain of x has been changed, then we might need to add things back onto the to-do list. So, and then we have a new domain, and we're going to eventually return this arc consistency one. Okay, so that's the arc consistency. And there are three possible outcomes when all arcs are made arc consistency. Either one domain is empty, the other one is each domain has a single value, or some domains have more than one value. And if one domain is empty, there are no solutions. We know that there are no solutions to this constraint satisfaction problem. If each domain has a single value, there is a unique solution. And if some domains have more than one value, there may or may not be a solution. So this isn't really solving the problem in general all the time. It's all that it's doing is simplifying the problem so that it can be solved more easily. So what do we do when we finish? So if some domains have more than one element, what we're going to do is we're going to search. So we're going to end up with another search space here. And the easiest way to think about this is we're going to split a domain and then recursively solve each half of it. And it's often best to split a domain in half, and then we're going to keep going. And the question we're going to ask in class is, do we need to restart from scratch? So going through lots more examples in class, I'm going to play with this and see what happens. All right, thank you all.